Okay, so our next speaker here, we have Lee Prewitt, and we have Mike Allison at Samsung, who has a chair who's about to fall apart, I think.
Don't go over backwards.
Yes. So.
All right, thanks everybody. In this one, we're going to talk a lot more about some of that human readable debugging information stuff, going basically down to the next level. And again, you know, Lee Prewitt, I'm a senior director in cloud hardware storage at Microsoft, and Mike Allison is the senior director in NAND product planning at Samsung. And basically, he is the lead editor. Hold on. Is it not? Was it there? I think it was there and went away.
Okay.
Right? Oh.
There you go.
Great, thank you. And so for those of you who don't know, Mike Allison is pretty much the lead editor for the NVMe specification itself in NVMe. So with that, I want to kind of, again, set context. I guess I'm the context guy today. You know, these fleets, they contain millions of drives now, and you know, tens of millions of drives really, across the world, multiple regions. Even small issues can have big effects, right? So, like many of you heard me say before, 1,000,000 to 1 chances happen 9 times out of 10 at scale. So we have to be able to quickly identify what's going wrong before it becomes pandemic in the fleet, and understand exactly what dig down into it very quickly through data, and get that back to the vendor and get the vendor working on figuring out the FA and getting us a solution. So, you know, data centers are highly restricted. Again, we've talked about this multiple times. I've got anecdotes about how, you know, we're trying to get a drive out of the data center and it just don't, you know, the security says, no, it's got to be shredded. So with that, then it's like the next level is like, well, what about getting the log files that a lot of people, they have either, you know, it's all in binary, usually it's also encrypted, and that sort of thing. And so our security guys can't take a look at it. So again, that's a good no-go. We need to figure out how we can get it in such a way that it's got enough human readable information that we understand what it is, but it also has enough detail for the vendors to be able to debug it. So it's like, how do we undo this whole process so that, you know, again, the next level, maybe we could do this like, well, it comes out of the drive in binary and we have on-site a vendor tool that decodes it into something that then can be exfiltrated from the data center. But that doesn't really scale. We've got 5, 6 vendors. We've got every new model that comes out would have to have a new version of the tool, these sort of things, and don't scale. And again, our security guys go, well, where's the source code to that tool? I want to make sure that it's not doing anything hinky inside my data center. So, you know, it's like right now with the processes and tools we've talked about here, things take weeks and months, and we need them to take days. And so that's kind of why with the process that we've done in the 2.5 for the telemetry, we're hoping that cycle becomes that days again. So with that, you want to take
now it's my turn, yes. So when we say telemetry, we're really talking about the NVMe Express telemetry host-initiated log page and the telemetry controller-initiated log page. And if you know NVMe, it has 4 regions. Data area 1, 2, and 3 were initially in the spec, and now there's this optional data area 4. Data area 4 was added because there was space limitations and they needed it to grow. So for this telemetry that we're talking about in this, it's about formatting data area 1 and data area 2 to a specific format to extract data. Data area 1 is going to be fixed in size, and it's meant to be very limited to affecting the I/O bandwidth happening in the device. Data area 2 gets to be vendor specific as to how big it's supposed to be, and it can affect latency when abstracting the data out of there. One thing that you have to understand is there is a TP that I was the author of that allows the get log page command in NVMe for the telemetry host-initiated log page for the host to say, hey, go collect a telemetry log page, but only include a certain set of data areas. So you can say, just collect data area 1, collect data area 1 and data area 2, collect data area 1, 2, and 3, or 1, 2, and 3, 4. So when the host initiates that command, they say, go generate it, and then I'll read it back. Without this change to NVMe, if you have tens of millions of drives and you say go collect telemetry, it's going to go collect all of it, and that takes time. And if you're just trying to get out this debug information and you don't need the full dumps that are in data area 3 and 4, then it's just a lot of time. So now the hosts can go in and say, no, I just want to collect the stuff that OCP defines in data area 1 or data area 2 and not collect the big bulk of data in data area 3 and 4. This is already ratified. It's available in the spec today. And I will give some insights into the the 2.5 spec that's coming. This will be a requirement that you have to support in order to use this. As I said before, these are the telemetry log pages. There's the data area 1, 2, 3, and 4, all defined in the NVMe 2.0 base specification. The header has a location, where to find the data, but it always tells you where the endpoint of the data is, and one data area starts at where another one ends. It doesn't do the normal, hey, here's your start address and length kind of areas. So now I'm going to get into what are the formats of the data area 1 and 2. So when we're going to expand data area 1 here, and you're going to see that there's going to be a header that's going to describe what's going on from an OCP perspective that's independent of the NVMe header in the original telemetry log page. And then there's a thing called statistics. Think of this as just variables. You can dump variables out. And then there can be 0 or more FIFOs. And FIFOs are just a way to have events. And since it's a fixed size, if you don't use the full fixed size, then you could zero fill to the 16K size limit that they've done. The header also tells you the location relative to the log page where the individual components live and their size. So this is a little bit different than what NVMe did to the data areas. This is the normal start and length type of paradigm. If we dig into the header has, hey, I'm this version of the specification that I'm doing. It has this thing called profile information. What I'm about to show you is a format for data area 1 and 2, and you could have one profile that says this is what I'm going to put in statistics and FIFOs. I could have a different profile that actually changes what you're going to put in. You can increase the number of statistics, you can change your FIFOs, and then the host is going to be able to select which profile they would want. As an example, you could have a default profile that you use, and you can have an extra debugging profile that dumps a lot more data, and they can swap between them. And you're not limited on 2 profiles. You can have more than 2. The spec, it's a spec, so we have ability to scale. And then in here, you also have information about the statistics for the current profile that the log page is associated with, and then there's the smart log pages associated when the telemetry log was collected. So let's expand now into the statistics. The statistics are variable in size. There's an array of them. It's a set of them. It could be 0 or more. The number of entries in there is totally up to the vendor of how many entries they need to be put in there. And then if we look at an individual entry, you're going to find that it has several pieces of it. First is the identifier. The identifier identifies what that entry is. And there are 2 things associated with the identifier. OCP is going to predefine some kinds of variables that you could put in here, or you could put in a vendor specific. When I get into my talk later, when I talk about how do we debug these and do the human printable part, the human printable part is for the vendor specific stuff. Anything that's defined by OCP, we know its definition. The parser can already know what it means. It doesn't understand vendor specific, and I'll get into that in a little bit later. Persistence is just telling you on that variable, what's its life? Is it forever of the life of the drive? Is it get reset on every controller level reset? And various other types of persistent factors there. The variable could also be associated with the namespace or not associated with the namespace. And if it is associated with the namespace, it'll tell you which namespace this particular data is part of. And then finally, you get into the data size, which is the entire size of the field, and it is dependent on the identifier of how big it is. You could have a byte, you could have 4 bytes, different sizes there. When we look at the FIFO again is just a thing of an array of entries. The entries are variable in size. You can start seeing this pattern here of it's very consistent on the pattern. When you look at it though, now you're going to see that there is a tuple of information in terms of identifying the actual entry. The first is a debug type. And the debug type is basically a classification of types of events. So they could be something about NVMe's defined events, PCIe, something about resets, something vendor specific. The identifier is an identifier within that debug type of what it means. So if I have a debug type of I'm PCIe resets, then an identifier of 1 is associated with the resets, and a different classification could also have an identifier of 1. So without the tuple of information, you won't be able to understand what it means in deciphering everything there. Data size is just telling you how big the entry is. Now, when you have an event that is OCP defined, the vendor can also add in vendor-specific information relative to that OCP defined event. And so we have a vendor identifier associated with that, and then there's also vendor data that goes along with that. Now, when we go to data area 3, you're going to see it has the same format as data area 1 in terms of the statistics in FIFOs. And so I don't have to go through and do a different format there. It has its own set of statistics that are dedicated to data area 2 and a set of 0 or more FIFOs that are dedicated to that particular area. In terms of where do I find all these, the initial header in data area 1 will tell you where all the locations are for data area 1 and for data area 2. And when I showed you the TP in NVMe that says, hey, I want to always dump either just data area 1 or data area 1 and 2, you always get data area 1 with the header, so you always know where all the offsets are to everything. So now, how do I go to dump this data out and create a human readable form? Well, you just start walking through the data areas and you go into statistics and you walk through them one by one, and if they're OCP defined, you print out the strings associated with that particular data, so you have the definition. And when it's vendor defined, then you have to go to the OCP strings log page and look up the string. So what goes into the OCP strings is the vendor specific identifier, and what comes out is the string, the ASCII string. The vendors define what the strings are in the strings log page. So let's look at the strings log page. String log page has a header. The header is to do versioning and tell you where these different sections are that are in the strings log page. The ones that are called table are basically a lookup of identifier to where in the ASCII strings does that string exist. So if you look at an individual entry here for the vendor statistics, it's an array that's sorted, smallest to largest, of each of the individual vendor-specific statistics identifiers. And if we go a little further and look at the entry, it has the actual identifier, and for each identifier there is a length, and there is an offset, and that offset is relative to the strings part of the page, and it tells you where the starting address, and you have the length, and you have the string. And when we look at the vendor-specific event identifiers, now this one here is if you have an event and the event itself says I'm vendor-specific, this is how you get the lookup for the string for this particular table. And then finally, we're going to look at the last one. And if you have an event that's OCP-defined event, but that event also includes vendor-specific data, then this particular entry is how you look at it, and you still see the tuple of information, so you can take the debug type and the vendor-specific identifier to look up where it is the string. So as you can see, this is, so the other thing I want to really say is, in this data area 1 and data area 2, the vendors defined what's in it. They got to figure out what statistics do I need to put in data area 1, what statistics do I need to put in data area 2, what FIFOs do I want where. The vendor picks everything. Nowhere in the spec is it going to tell you where to place certain data there. We said it at SDC 2023. It was stated, hey, debug your drives using this, and you'll figure out what you need to put in there if you're an implementer. There's also up to 16 FIFOs defined today that can be reported. You can put them all in data area 1, you can put them all in data area 2, you can just have one in each, you can have 0 and 1 or whatever. They're just an area of how big you want them and what you need to do, where you want to put them. One of the things about having 16 FIFOs is if you have multiple microcontrollers on there or multiple processes within your operating systems, you can use different FIFOs to try to avoid locking, and that's why there's 16. As I said before, there's different profiles, and when you have different profiles, you can just change how many FIFOs you're doing, how many statistics you're doing between each different thing, and then you also indicate how many profiles you support, and so they could figure out what numbers they could select from. The one thing is, that's important to understand is when you initially ship a drive, and you have that strings log page, and you could look up all the vendor-specific strings, and you do a later firmware update, and the strings log page that's in that firmware updated has to cover that image, that firmware image that you just loaded, plus the previous downloaded image. So when you have a drive and they dump the data areas the day they bought the drive, and 3 years later they use that drive's strings log page, it still has to decode the original telemetry that you did when it first bought it. So you can't go and reuse an identifier. It has to stay in there because they want to just keep using that drive's debugging capability and conversions to print out the human readable binary telemetry that they saved long ago, and they don't always have to just save the ASCII file. I am pleased to announce that Samsung has on the OCP contributions page, you can go look it up now. So if you go into the contributions and there's a search and you type NVMe, you're going to find a telemetry contribution of some scripts. One script is to parse these strings log page and the telemetry log page to what I just presented today. The other one is to create a strings log page and a telemetry host-initiated or controller-initiated log page so we could test the parser. The one for generating it, it is scriptable. It has an input file. You can say, this is how many FIFOs I want. This is how many statistics I want. You can put in OCP-defined ones. You can say, randomly generate a bunch of vendor-specific ones. The data that goes in there, though, is all random data, but it is properly formatted. So if we declare something that's 4 bytes, it'll put a random 4-byte value there. If it's an OCP-defined one, it'll look at all the definitions of the bytes and everything of what can fill in there. The good news is Samsung is committed to updating the NVMe CLI to support parsing out the telemetry log pages with this format. These scripts were used to help debug the code and generate it. So as soon as the spec becomes available on the contribution, then Samsung's ready to commit this there. So what I like to think of it is there's been a lot of concurrent engineering. By generating these scripts, we were able to validate the spec and how it aligns to data. And yes, we did find some issues as we went through this process. But then we're concurrently looking at, hey, we need NVMe CLI there day one when the spec is there so people can, when they're building their drives, they have the tools they need to do that. And this is because it's open, it's available. As we make changes or whatever, we can all work together to update the script. So I really do encourage you, they count the numbers, so go out there, look at it, open it up. And by the way, if you want to see what the actual data sizes are, it's all in the script, so you can see those before the document comes out. So with that, I'm encouraging you all to come to the OCP and discuss the debugging stuff, and this is all part of OCP and the debugging. Please come to the meetings, And with that, we will entertain questions, and I can't see anything with those lights. Any questions?
Hi, Mike. I'm struck by the really well done design that is setting up for use of non-ASCII, so you can support other languages. The separation of strings from the data is the crucial step to enable that, and then you can generate a localized file in another language. Has there been any thought along those lines in moving in that direction? And this is not about putting Unicode in the drive. This is about post-processing tools picking up a localized file that swaps in strings in, say, Korean instead of the ASCII strings in English.
We haven't had those discussions yet, but those are things that we could look forward to doing. We get to do a lot with this if we want to.
Yeah, cool. As I said, kudos on, I'm not sure how you got there, but kudos on doing the crucial I-18N internationalization work and what you have done that makes picking up a localization file later possible.
Yep. So yes, Dave, I think it's a great idea. It's not something we had thought of a priori as we were putting this all together, but awesome idea. I think
Yes,
I like that
and
a lot.
it's really cool. However you got there, you did the crucial step that's going to make that possible in post-processing tools. So nicely done.
Okay. Any other questions? Or am I that good? All right. Thank you.